Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we're going to extend the previous discussion into 3 dimensions. And we're going to actually start counting electron states that are filled. And we're going to develop a number of parameters that characterize this filling of the electron states. So to demonstrate an understanding of this material, it becomes important for you to be able to accurately carry out some of these calculations that I'm going to run through in this lecture. Because if you can carry out these calculations, presumably you understand the background material that has been used to develop these very important formulas. So this is basically going to be a lecture about counting electron states. We're going to recall our previous discussion about density of states. That turns out to be an important concept. And we're going to try to put all these ideas together and come up with some really important parameters that really characterize the electron states in metals. We're basically going to extend our discussion into 3 dimensions, and that's important because we have to count all the possible states that electrons can have as they move around in 3 dimensions. We're going to, up front, set the interaction potential energy equal to 0. When we do that, that basically is telling us that we have free electrons. We will relax that condition towards the end of the week, so we'll go back to our discussion of how to represent U, and we'll see what important new features that periodic potential introduces into the electron states in solids. So that'll come at the end of the week, and that's an important set of lectures to listen to, because they really once we put in the periodicity of the lattice, we really start to capture some of the important features of the electron states. In 3 dimensions, we're going to write down a wave function that now has a wave vector component in the x direction. We're going to call that k sub x. It's going to have a component of the wave vector in the y direction. We're going to call that k sub y. And it's going to have a component of the wave vector in the z direction. That's going to be called k sub z. And so if we write this wave function down and we put it back in the Schrodinger's equation, what we find is that the second derivatives with respect to x, y, and z just give these the sum of the k vectors, kx squared plus ky squared plus kz squared. And so this then allows us to identify the electron energy eigenvalues in terms of this quantity h bar squared k squared over 2m sub e. So this identification we've made many times throughout the semester, but I think now you can start to see how it comes logically from these definitions of wave functions in 3 dimensions. We have to talk a little bit about k-space and about the allowed k vectors that these electrons can have. And so to do that, I just remind you very quick about the 1-dimension discussion that we had. You recall in 1 dimension, the wave vectors, the allowed wave vectors, were 2 pi over L, where L is the length of the crystal, times some integer m squared, where m is a signed integer. So we can identify this parameter, 2 pi over L quantity squared times m squared. We can now identify that with the wave vector k in the x direction. So that turns out to be kx squared. And we've already discussed that these values for k sub x are not arbitrary. They only can have certain quantized values. And so we developed this chart, right, which is a schematic chart. It's not the scale, But what it tries to indicate is it tries to indicate that there's a very fine-grained structure. This fine-grained structure is given by allowed k vectors that are separated one from another by 2 pi divided by this wave vector L. And then every so often there's when one of these allowed k sub x's that are due to the cyclic boundary conditions that we impose, every once in a while one of these allowed k values happens to coincide with the reciprocal lattice vector g sub n, right? And g sub n is defined as 2 pi over a, 4 pi over a, right? So something special is going to happen when the fine-grained structure matches up precisely with one of these reciprocal lattice vectors. And that's an issue that'll be resolved at the end of the week. So I just mentioned that this diagram is not to scale at all, right? N is a rather large number. It can be on the order of millions to hundreds of millions, just depends on the number of atoms that you're considering, right? And so in principle, this fine-grained structure that I indicate by these discrete tick marks is hardly resolvable on this diagram. But I just sort of blow things up in a symbolic way to indicate that k space, that the allowed values of k sub x for electron states in one dimension, right, are really quantized. And the quantization is this 2 pi over L. So that's something that we've already discussed, and hopefully you understand at an intuitive level at this point in the course. We're going to extend that argument to 3 dimensions. Our 3-dimensional crystal now is going to have a dimension L in the x direction, a dimension L in the y direction, and the same dimension L in the z direction. That just makes it a little bit simpler to handle the arithmetic. So we're going to require this cyclic boundary condition that the wave function at some point is equal to the wave function at x equal to L. That gives rise to this quantization of allowed k values, and now it's in the x, it's in the y, and it's in the z direction, right? So these parameters mx, my, and mz, these are quantum numbers associated with each state, and they are signed numbers, right? So in principle, they could be plus or minus a certain value. And what we often do is we often write this fine-grained structure in the energy eigenvalues E sub m. We often write that in terms of k squared multiplied by this familiar h bar squared over 2m e prefactor. And we start to label each energy E by its quantum number k. So this wave vector k is going to take into account the quantum numbers of each of these states in a symbolic way, right? So at the bottom of the slide, I just sort of summarize what I've tried to say, and in particular, I'm trying to make the point that the allowed values kx, the allowed values of ky, and the allowed values of kz are all going to be 2 pi over L, where L is the length of the crystal, times integers, and these integers are labeled as mx, my, and mz. What you can do, once you understand that, is you can start to talk about the degeneracies of these solutions in 3 dimensions. And I try to illustrate that schematically in this slide for just a few select values, because clearly mx, my, and mz are going to range up into the millions because we've got so many electrons that we're trying to count for. But if you understood what I said in the previous slide, then you'll understand that this is the expression for the energies. This expression is subscripted by the index m, which tries to symbolically represent the specific values of mx, my, and mz. So what we can do is we can rewrite mx squared plus my squared plus mz squared. We can rewrite that as capital M squared, and then we can start to make a table that lists the possible values for m squared and how those possible values for m squared are actually made up by the individual quantum numbers mx, my, and mz. So it's pretty simple to start with capital M equal to 0. With capital M equal to 0, that means mx, my, and mz also have to be identically 0. So that means that there's only one way that that particular state can be formed, and that one state is going to be twofold degenerate when we include spin. So this energy state is going to occur at 0, and it's going to have a degeneracy of 2. When we go to the next highest value of capital M squared, the next highest value would be capital M squared equal 1. That can be made up by having m sub x equal to plus or minus 1, m sub y 0, and m sub z 0, right? So there's two ways to make up this m squared equals 1 state, the plus minus 1 in m sub x. But that's highly degenerate because the quantum number plus minus 1 could either be an m sub y or an m sub z. And so that means that we pick up a factor of 3 in the degeneracy of this particular energy level. So this particular energy level, characterized by m squared equals 1, has got a degeneracy of 6. 2 comes from the plus minus value here. 3 comes from the fact that we can distribute that value of plus minus 1 in 3 possible ways. To go from the degeneracy to without spin to the degeneracy with spin, we have to include another factor of 12. So that next energy state actually has a degeneracy of 12. And I work out the first few items in the table, and then you can actually start to make plots which indicate the number of electrons with upspin, the number of electrons with downspin as a function of energy. The energy eigenvalues are equally spaced by this quantity delta E, and delta E is just this h bar squared over 2m times the quantity 2 pi over L squared, right? So each of these energy levels is equally spaced, and they can hold. They're highly degenerate, right? They're highly degenerate. The degeneracy depends on the quantum numbers that are chosen. Sometimes it's useful to visualize this degeneracy in 3 dimensions. So I just include that plot here. Maybe if it helps you understand things, that's great. Here I've got a coordinate system where I'm plotting the allowed values of m sub x, the allowed values of m sub y, and the allowed values of m sub z. And I just indicate the first few contributions to these quantum numbers. So for instance, for the m squared equals 1 case, the degeneracy is equal to 6. And you can see that these 6 red dots, okay, that I've got drawn here, happen to fall on the values of m sub x equal plus minus 1. So here's plus 1, here's minus 1, here's m sub y equal to plus minus 1, here's the plus 1, there's the minus 1. M sub z could be either plus minus 1, so here's the minus 1, here's the plus 1. All of those states indicated by these quantum numbers being occupied, they all give rise to the same energy, and it indicates that without spin, that state is 6-fold degenerate. When you include the degeneracy of the spin, then each of these dots, each of these quantum states represented by those red dots would hold 2 electrons. Okay, so that's clearly the advantage of this type of plot is you can start to see how these electron states are organized in terms of the quantum numbers. By now you should understand this concept reasonably well. What we really want to do is we want to count how many states there are, and then we want to ask how many levels are filled, because we know how many electrons we're putting into, let's say, a cubic meter of a metal. We calculated that in the last lecture, so we know how many electrons there are per cubic meter. If we know how many quantum states there are per cubic meter, we can then start to account for how many of these quantum states are actually filled. And the way we do that is we use the combined quantum index capital M, which is now going to be the square root of the mx, my, and mz squared. We use this guy to count our electron states, right? And so if you go back to the previous slide, right? If you go back to the previous slide, we can solve this expression for the quantity mx squared plus my squared plus mz squared. That's exactly what I've done here, right? We've got this equation, which I call equation 1. And then we can start to make plots in our quantum number space. We can start to make plots, and we can calculate all the electron states which have an energy less than E, right? And E is subscripted with capital M, and that's the quantum number that characterizes that particular state. So I've drawn the characteristic diagram. We've seen this 2 or 3 times already. I don't include the third axis m sub z because it starts to get very complicated. But in 2 dimensions, mx and my, each quantum state is indicated by a dot. There's a box around each dot. The dimensions of the box are given by 2 pi over L, and that's basically telling you the area in 2 dimensions that particular state requires. When you include the third dimension, these squares turn into cubes, and these circles turn into spheres. And the question then becomes, how many of these quantum states lie between, let's say, the quantum number capital M and the quantum number capital M plus delta M. And we're going to just go through this derivation rather quickly, because in principle it's just a question of counting dots within shells and taking appropriate derivatives. So we like to ask, what is the maximum energy allowed for electrons that are dumped into this metal? And the number of and the maximum energy that's allowed is going to depend on the total number of electrons in the system. So we've already calculated the total number of electrons in the system. That's capital N. That's a number that we've already calculated. It's going to be equal to a factor of 2 for spin times the total number of states possible, right? And the total number of states possible is going to basically just be given by the volume of a sphere with a quantum number capital M max cubed, right? So this is the volume of the sphere. This is the factor of 2 that includes the number of quantum states. And when we go back to equation 1 and substitute in an expression for M sub max in terms of the maximum energy E sub max, right? So we make use of equation 1 from the previous slide, and we just solve this equation for E max. And that's all that I've done here. And at the end of the day, we find out that in order to accommodate these N electrons that are dumped into the system, the maximum energy that the electrons can have is going to be just given by this quantity. It's this familiar h bar squared over 2me times 3 pi squared times the number density, N over V, of the number of electrons contained in this solid. And so this expression here, 3 pi squared N over V raised to the 2/3 power, that's often written as K max squared. And we've got this very nice expression now between the maximum K vector allowed and the number density of electrons in the solid, right? So this is an important argument. you should understand it at a very fundamental level now, because we've done it 2 or 3 times for different systems. We've always done it for different systems. Now we're doing it for free electrons in a metal, and we've got an expression now that tells us the maximum K vector that an electron state can have in terms of the 1/3 power of the ratio of the number of electrons per unit volume. So that's a very nice result, right? And that is a fundamental result for a free electron model in metals. And on this slide, what I just do is I just evaluate some of these numbers for the case of sodium, because we've already worked out some of these factors. So, for instance, this maximum energy is often called the Fermi energy of an electron in a metal, and it's abbreviated as E sub F. It's given by this expression here. We've already calculated the ratio of N over V in last lecture for sodium, so we can just substitute that number in a very straightforward fashion. And what we find is that the maximum energy for these 10 to the 28th electrons per cubic meter in sodium, the maximum energy they can have is 3.09 electron volts. We can calculate the maximum wave vector, K sub F. And again, this is K sub Fermi. We can calculate that using the equation on the previous slide. And we can find that that number is about 9 times 10 to the 9th inverse meters. It's very useful to calculate how big K sub F is compared to this first reciprocal lattice vector, G sub 1, right? So we calculate G sub 1 by knowing the lattice constant of the distance between atoms in a sodium crystal. We take the ratio of K sub F over G sub 1, and what we find is that the maximum wave vector that electrons can have in a sodium metal comes out to about 0.6 of the first reciprocal lattice vector, G sub 1. We can also calculate the Fermi momentum, right? The Fermi momentum is just h bar times the wave vector K sub F. We get a number for that. Knowing the mass of the electron, we can estimate the velocity that this electron is going to have. So the velocity of the electron in the free electron model for the most energetic electron in sodium is going to be about 1 times 10 to the 6th meter per second. So these electrons, when they become detached from the individual sodium atoms, are moving around in the crystal with a velocity of about 10 to the 6 meters per second. And then lastly, we like to make contact to the de Broglie wavelength, which we discussed very early on in the semester, right? The de Broglie wavelength for this most energetic electron is going to be related to 1 over the momentum of that electron. We have to multiply by h, right? When we work through those numbers, we get a number about 0.69 nanometers, and we compare 0.69 nanometers to the lattice constant of 0.42 nanometers for sodium, and we get a ratio of about 1.6, which means that the de Broglie wavelength of an electron moving in sodium is about 1.6 as large as the unit cell. So it exceeds the unit cell of sodium. These electrons are truly quantum electrons. They are delocalized from individual atoms in the sodium crystal, right? And that's what this ratio of the de Broglie wavelength of the most energetic electron to the lattice constant A. That's what this number's trying to tell you about. It's useful to summarize these results in the table. I do that here. It's also useful to step back and think about what these results mean in the context of the model. So what we've just calculated is that if you have a crystal that's got a length L, right, you're going to have 2.5 times 10 to the 8th, 2.5 times 10 to the 28th electrons per cubic meter in that crystal. The electrons are going to fill up energy levels from the bottom of this well up to a height of 3.09 eV. So this 3.09 eV is measured from the bottom of the well, which defines equal to 0. And each of these free electron states will be delocalized over the entire crystal, right? And the separation between these energy states is going to be extremely small, right? And so this is now the picture of electron states in a solid based on this free electron model. Closely spaced energy levels delocalized over the entire well of the crystal structure. It's often useful to visualize these electron states not in real space but in K space. It turns out that has a lot of advantages. So it's useful to plot the allowed electron energies versus this wave vector K. So here I plot just as a function of Kx. It could be Ky, it could be Kz, right? But let's just say it's as a function of Kx. These special reciprocal lattice points, 2 pi over a, those are marked on this diagram. The energy follows a parabolic, the allowed energy of the electron states follows a parabolic relationship because E is equal to h bar squared divided by 2me times k squared. So this red curve is a parabola. All the electron states from E equals 0 up to the Fermi energy are filled. Fermi energy lies at 3.09 eV above the 0 energy level, right? And you can see that the maximum wave vector, K sub f, the Fermi wave vector, only is about 0.6 times this reciprocal lattice vector 2 pi over a. So for the case of sodium, the electron states don't even come close to these special values designated by the reciprocal lattice vector. When they do, very interesting things happen, right? And that'll be discussed later on in the week. If you blow up a region of this curve, and I do that here, right? What you find is that this E versus K squared dependence really is comprised of individual quantum states. Each quantum state can hold 2 electrons, and the separation in energy between these quantum states is given by this quantity here, right? You can calculate what that separation in energy is between the allowed K values, right? And you find out that the separation in energy for sodium is really very small. It's infinitesimally small. For instance, if you have a crystal that's, let's say, 1 centimeter cube, right? The separation delta E is 10 to the minus 33 joules, which essentially is 0. And it means that to a very good approximation, these electron states are continuous function of energy E throughout this E versus K curve, right? So I think that kind of ties up the whole story, and it gives you a connection back to why these electrons are referred to as free. The quantization of the electron states is essentially insignificant, right? It's insignificant on the energy range imposed by the filling up of the states. So this energy range is about 3 eV, and on that energy range, this 10 to the minus 33 joules is a really small number. So this Fermi energy, okay, let's reiterate, make sure this is clear. This Fermi energy of 3.09 eV, this is the separation between the filled states and the empty states of electrons in sodium. This boundary between the filled and unfilled states is very sharp at T equal to 0. When you start to have finite temperature, this Fermi energy starts to become blurred, and that'll be a topic of discussion in the following lectures. So we'll have to wait until a future lecture when we actually put temperature into this calculation. So it's important for you to be able to do these calculations given some of the relevant parameters. If you can do these calculations, that demonstrates a basic understanding of the material that underlies it. So it's important for you to go back and review that slide where I calculate various parameters. So that's all I wanted to say for today. When we come back, we're going to talk more about the temperature dependence of these occupied states. We'll start to put temperature into the problem, which means that you're going to see a Fermi-Dirac distribution function in the next lecture. So we'll see you whenever you have time to take a look at that set of lecture notes.